Welcome back to this NPTEL online certification course in the molecular rearrangement and reactive intermediates. In the last class, I started talking about benzyne, and I have shown you there are several methods how you can make benzyne. In the today's class, my main focus is what are the different reaction about benzyne. We are going to learn about different type of reaction which was done using benzyne. So I'm going to show you the reactions of different type of pericyclic reaction. That will be see the major type of reaction you are going to see using benzyne. And then there are some sort of arriation reaction. I think I already talked about some of the reaction when I was starting with the benzyne, that if you use some sort of a phenyl lithium which is actually used for the formation of benzyne, at the same time it can act as a nucleophile. Okay, so let's start with first with the pericyclic reaction. So I'm going to talk about the different reaction about benzyne. Okay, so I think as I mentioned, in the today's class my main focus will be the pericyclic reaction. Okay, I'm going to talk about some of the 4+2 and 2+2 and then some of the in reaction and 3+2 reaction, and then there will be other reaction is the arriation reaction. I'm going to talk about some of the reaction today and some of the reaction in the next class. There will be insertion reaction. I'm going to talk about some of the molecular rearrangement using benzyne, multi-component reaction, and very briefly about the transition metal catalyst reaction. So let's start about the pericyclic reaction. We all know about in the 4+2 cycloaddition, and we have already learned this in the in the pericyclic reaction course. So here what is going to happen, if you have remember the 4+2 cycloaddition, we always talk about, so there will be a diene and there will be a dienophile. And if you remember, we always mention the dienophile will have an electron withdrawing group, and then diene will have an electron donating group. Okay. So now you can see that so, and then we also talk about, if you remember that this cannot be always a double bond, there can be also a triple bond. If you remember, we always talk about these type of things when we talk about, it could be H or it could be R or R dash. So again, I think we already talk about this type of reaction in the pericyclic course. So here what is going to act, so that your benzyne is going to act as a dienophile. So now if you take a diene and heat up, it is going to participate in a Diels-Alder reaction, a 4+2 cycloaddition reaction, to form this product. Again, I think if you see the major difference here, what is happening in every single product, your one benzene is going to get attached. If you remember, in case of the 4+2 cycloaddition reaction, we form a corresponding cyclohexane with a cyclohexene we form, correct? Here what is going to happen with the cyclohexene, you see a benzene is going to get attached. Again, the all the rule what you have learned for the 4+ cycloaddition will be remain same, that here once you have a substitution here, so here you have a methyl, and if you remember once you talk about the 4+2, they come in a facial approach of both the dienophile and diene. So both the groups here in the diene which are substituted here will be up. Okay. Again, this reaction will be more reactive if you have some sort of a diene, like if you are in the ring like furan or the cyclopentadiene, what is going to happen, these are even, so in case of the cyclopentadiene, if it is a ring form versus a chain form, like open form versus a closed form, the closed form will be much more reactive, because you can see this is already in the cis-OID conformation. In case of, if you have a 1,3 diene, then in that case you have to kind of, there has to be a rotation to make sure that they can be in the cis-OID conformation for the reaction to happen, correct? But here this is going to happen. So now it can form this 4+2 product. Here also, if you have a furan, it can also go through the 4+ cycloaddition to get to this corresponding product. So I think if you have learned in the 4+2 cycloaddition, there are two different type. One we talk about a normal 4+ cycloaddition. One we talk about a inverse electron demand Diels-Alder reaction. I think we also talk about the difference, correct? That once you talk about in case of the normal Diels-Alder reaction versus the inverse electron demand Diels-Alder reaction, the one of the difference you have seen the type of the functional group or the nature of the diene and dienophile. I think in case of the normal, we talk about that here will be electron donating group, some sort of electron donating group will be here, and there will be electron withdrawing group. But in case of inverse electron demand, you will see there will be electron withdrawing group attached here. It could be attached in the terminal position, or you will see there could be a nitrogen will be here in this position, which can be pulling electron density like some sort of imine, or you will see some case instead of electron withdrawing group, you might see some case of carbon group here. and now you will have a electron donating group here. So this is a the inverse electron demand. So now you can see as you see for in case of the benzyne, there is, if you think about a benzyne as some sort of a deuterium, some sort of a cation and a anion, that means it can act as a dienophile for both type of reaction, for a normal Diels-Alder as well as for a inverse electron demand Diels-Alder reaction. I think this type of reaction already taught you in the inverse electron demand reaction. Here what is happening, the benzyne is acting as a dienophile. So once the benzyne is acting as a dienophile, first after the 4+2 cycloaddition it is going to form this compound, but this is not to stay there, because this is going to release N2. So there will be, you can see this arrow push to form this N triple bond on end. So that will remove the N2, then this bond going to form, the new bond going to form, and at the end you end up generating a isoquinoline. Okay. There is another example here. I think we start from this compound and generated this N2 plus and COO minus. Okay, and then what is going to happening, now it is going to generate the corresponding benzyne. It is very similar in this anthranilic acid scenario here. So if you have this anthranilic acid, it is generating this corresponding benzyne, and now it is participating in a Diels-Alder reaction. Again, you can see here, you will see that in this particular cases, your diene also have electron withdrawing group attached. Okay, so so this can participate in a 4+2 cycloaddition, and then after that there will be a release of CO2. So this part we will going to get out. So this 4 carbon, 1 2 3 4, and then this benzyne will have this 1 2 carbon. So now you can see that these 4 carbon here, 1 2 3 and 4, and this will be your 1 and this will be your 2, and then the CO2 getting out to form this corresponding product. So there is another important reaction here. So starting from the tropones, so the tropones can be also used in the Diels-Alder reaction. You can think about the tropones having this type of you can see 2 double bonds in a cis-OID form, so that can participate in a Diels-Alder reaction to form this bicyclo nonatrienone structure, bicyclo 322 nonatriene. So you can think about sometimes people write this type of mechanism, but you can also think about some sort of a concerted way of forming this product, or you can think about writing as a, because if you think about there is a plus and minus, then this can attack here, this can push the electron density and attack here and form this product, or you can think about, as I mentioned, like a like a pericyclic reaction through a concerted mechanism. But again, what is happening, there is two different, if you think about this molecule, one of the important fact is there is two different set of diene. You can consider this is a one set of diene, and this is other set of diene. So it can, the reaction can happen from the both sides, so you end up making both the products here. Okay. And we also know that about the formation of this benzyne from here, how the benzyne is forming. I think this is a Kobayashi's technique. I have already taught you in the first lecture that cesium fluoride is going to attack to the silicon, then it can go for elimination of this triplet to form this corresponding product. So Professor Biju from ISC, he discovered this reaction, that if you start with the corresponding styrene, and then again you are using this very similar the benzyne you are generating from the Kobayashi's technique. Now they can take part in this type of 4+2, and then there will be a yin reaction happening, which is a concerted process, correct. So this another molecule of the benzyne giving electron density here, and this is I think what you have learned in the yin reaction, if you remember, that this this hydrogen going to find. So if you think there is a enophile, generally if you have learn about the yin reaction, we have taught you the carbonyl yin reaction, where you have a carbonyl which can take the proton, and then the other side is going to get attacked. So the very similar thing happening here. Okay, here you have the benzyne. You can think about benzyne as a plus and minus, then you will get your answer. And then after the concerted process, it is forming this corresponding product. Again, benzyne, the other thing is, if the benzyne can participate in a 2+2 cycloaddition, but the 2+2 cycloaddition reaction when it is happening using the cis or the trans, they are giving the they are giving. So if you use the this 1,2-dichloroethane, if you cis versus a trans, what is happening, you end up still getting the similar type of product selectivity. You still able to get the both cis and trans. So that means the both syn and anti, sorry. So this will be your syn and this will be your anti. So using this, either using the trans or cis, you end up getting the mixture of both. So now the question comes, what is happening here? So this is going through some sort of a diradical formation happening. Okay, so it is formation of the some sort of a diradical happening. That's why once you have this diradical, there is a chance of the bond rotation. As there is a chance of bond rotation is happening here. So if you think about the bond rotation is happening, that's why I think in this case, because of the bond rotation, you end up getting giving the mixture of products. So you end up giving to the both anti and syn product is going to form. Okay. So the other thing is the benzyne is also known that if you are forming benzyne and if you have nothing else in the reaction, benzyne can dimerize themselves, okay, to form this biphenyl phenylene. So it can form this biphenylene, and it was already confirmed. If you are doing a some sort of a reaction using benzyne, and if you will see some sort of a byproduct of biphenylene is forming. Other important reaction that if you have a if you have a benzyne, now the question comes, if you are trying to do a reaction, a 2 plus some sort of a 2 plus 2 type of reaction using this some sort of a vinyl OTMS group is here. So what is going to happen in case of the butyl lithium? First thing is it is going to generate the corresponding the benzyne. Now it is going to go for a metal halogen exchange to generate an anion here. It will be a minus. Now the triplet is going to get out, and it is going to generate the corresponding corresponding benzyne here. So now the question arises that where the nucleophile is going to get attacked, because now if you have this part, you have a head and you have a tail. So it is going to form form the bond with head with head, or will be head with tail. So that is the question we have to answer, because the product we are seeing, it is a head to head product formation. So what is happening here? Now if you think about that, we already taught you that if you have a OME group, then it has an inductive effect, correct? So now if you think about a mechanism where you can either think about forming bond here, now you can think about when it is attacking, it is going to prefer attacking in this position, because now it will generate a minus in this position. So it is going to generate a minus in this position, so that is going to be stabilized, correct? If you remember, I told you that if you have a OME group, it is have a minus A effect, it is going to stabilize the anion in the ortho position. So that's how now if you is attacking from this side, you can see here, once it is forming, then now this you are generating a negative charge here, which is going to attack here to form this corresponding product. The mechanism is shown here, that as I mentioned, first you form this benzyne, and now you can think about that there will be two possibility here. It can either go for intermediate like this, where it can attack from here, or it can form some sort of intermediate like. You can think about that this intermediate can be written in the two different ways. You can write a positive charge. So of course there will be that this negative charge will be in the ortho position, that is confirmed. Now the question, you can write a intermediate where there will be positive charge in this position. That means what I was trying to show you, that it is going to attack. We already know that if you have this type of with the silicon and R, then this we already know that these are already in the stage of a, it's some sort of a TMS enol ether, which is going to take part in a reaction through this. So that means if you think about intermediate A, which will be much more better stabilized, because you are generating a positive charge next to oxygen. Okay, so it's going through this intermediate, it is going to form this product. Then there is another important reaction, another 2 plus 2 reaction again. What we are saying here, that after the the benzyne formation from the Kobayashi's method, you have a some sort of enamine. Again, if you remember the reactivity of enamine, we know the reactivity of enamine, that it is going to react something like this. It will be going to generate this minus here, which is going to add to this imine and going to form this corresponding product. Okay, so I think I can write it down here. Taking here and forming the corresponding, and you have a R1 here, of course, forming the corresponding product. Okay. Again, there is another method of 3 plus 2 cycloaddition happening. So starting from here, using the benzyne, and if you use this TMS diazomethane, it is going to form this product here. Let me try to understand what is happening here. First thing is, if you have this lithium TMP, if you not know what is the structure of lithium TMP, I am going to show you. This is a tetramethyl here, and there is a lithium on the nitrogen. So it is going to look like something you have, something means you have some sort of a hindered base here. That means it can only go for a proton abstraction. So it's going to act as a base, not as a nucleophile. So if you act as a base, what is going to happen? It is going to abstract the proton from here. It's a very strong base. Okay. Then what is going to happen? It is going to form a benzyne, and now this corresponding lithium which is there, because this lithium TMP can also abstract proton, okay, from this. So this CH in the so this you can think about. So this proton is going to get abstracted in the inputs of lithium TMP, going to get from a lithium which is going to attack to the benzyne, and now it is going to form this negative here, which is going to come back and attack in the nitrogen to neutralize the charge to form this compound. And again you have a lithium TMP already in the reaction, so that can now going to abstract this proton which was there to form this lithium, which can now form this carbon nitrogen bond and form a N minus from here. So you will see there is a silicon here, TMS group, and a minus which is going to take a proton to get to the corresponding product. So now I am going to talk about this 3+2 cycloaddition reaction. Here you can see here starting from this corresponding the TMS triplet, we can generate this corresponding benzyne using the corresponding Kobayashi method. Now you have this compound here which can be synthesized from the corresponding carbonyl and the hydroxylamine. And now once you have this compound, what is going to happen? This is going to first going to attack to the corresponding benzyne, because the nitrogen have a lone pair. It is going to attack to the benzyne, generate this compound. This minus can take this proton to form this sort of intermediate. And now you can think about once you are forming this, this is again becoming a 1,3 dipole. You can write them 1, 2, 3. So this 1,3 dipole can take another benzyne and then going to form this product. Okay. So it is happening there. First there is a 3+2 cycloaddition. First there is a attack of this nitrogen, then there is a 3+ cycloaddition happening in this stage to get to this product. Again there is another important method here, again using this different type of diazomethane. So what is happening? Again, if you remember that if you have diazomethane, we always think about there is a negative charge. Okay, so this can attack here to the double bond, correct? And then what is going to happen? This can come back and add here. Okay, it can form this, and then further what is going to happen? There is this proton can be abstracted to form this corresponding NH. It will be N minus, and it is going to take proton to corresponding NH. So there is a example here, the double benzyne in reaction happening. First there is a formation of benzyne from this corresponding deuterionic from the starting from the anthranilic acid. Once the benzyne formation is happening, what is happening here? This can, so first thing is it can take this in the methyl proton here from the benzyne have a, if you think about a plus and minus, then it can take this proton here through very similar to the corresponding in reaction. Now it can take the positive part. And after that, what is going to happen? In this stage, there is another benzyne can take part to participate in another round of in reaction here. So it can act as a enophile to form this corresponding product here after the two successive in reaction. Now I am going to talk about the so I talk about some of the pericyclic reaction. Now I am going to talk about the arylation reaction. So starting from this 1,2-dibromo-benzene, if you use a butyl lithium, it is going to go for the metal halogen exchange to generate the corresponding lithium here, and now it can able to react with another compound. So it can so I think this can form a benzyne, and this can attack here. You have seen in the mechanism. First thing, the metal halogen exchange, formation of the benzyne, then this corresponding lithium which is formed in the reaction going to attack to the benzyne to generate a corresponding lithium which can take a bromine from the corresponding dibromide to get to the corresponding product. Then there is a another reaction where the oxazolene can act as a directing group. I think I am going to talk about this, about the the directing lithiation, when I am going to talk about the organolithium compound. Using a directed lithiation, you can able to form this corresponding lithium here by removing this carbon hydrogen bond. It can form this corresponding lithium. Now what is going to happen? It can get rid of the corresponding chlorine to form this benzyne. So here if you take a phenyl lithium in the reaction, the phenyl can attack here, and this corresponding lithium formation is happening here, because this can stabilize this corresponding negative charge formation happening in the ortho position, which can further get protonated to this compound with a very high regioselectivity. Then you can see in a very similar reaction here, you have the bromo and the iodo. So first the weaker the carbon hydrogen bond going to get cleaved in place of the butyl lithium, so metal halogen exchange. Then after that, what is going to happen? It is going to get rid of one of the bromine to form this corresponding arynes. So now what is going to happen? Once you form the aryne, you already have this corresponding lithium in the reaction. So this lithium can act as a nucleophile and going to attack here. You can see here, this is going to attack here to form this sort of a intermediate species, which is going to take the the iodine from the butyl iodide. If you add a butyl iodide, this lithium can take iodo from there to form this product. Okay, because you can see what is happening in the reaction medium. Already you have generating a butyl iodide, because you have a butyl lithium here. First thing, you have a once you have a butyl lithium, you have this N-butyl iodide, and then that N-butyl iodide was there. So there you can see that again this can getting exchanged here, get to this corresponding product here. The other important technique is that if you have this corresponding benzyne, if you have generated from the Kobayashi's technique, then if you add a corresponding nucleophile, suppose if you have a benzyne like that, and now we are talking about a nucleophile. Suppose you think about amine as a nucleophile. So if it is a primary amine, okay, then what is going to happen? This is going to attack here. Once it is going to attack, if you remember, it is going to form some sort of anion here, minus, plus. Now this can take this proton from here. Okay, so after you form the product, what is your product? In the product also you have another H here and NR. So this is not going to stop here. So if you take a primary amine, this can take part another reaction with a benzyne. You can take another benzyne and do very similar type of reaction. So at the end, what is happening? You end up forming a tertiary amine, and you have two aryl ring here. Correct. So you can see here, if you started here with this type of primary amine, you end up making a product where you have two different aryl ring which is attached. You are making a corresponding tertiary amine. And if you started with a secondary amine, then there will be one benzyne going to get inserted to get to the corresponding product. Again, very similar thing here. You have a secondary amine here, and you end up getting one benzyne getting inserted. If you have primary amine here, you will get two benzyne getting inserted. So you end up making it corresponding tertiary amine. Now the question comes, what about other nucleophile? What about thiol or phenol or the carboxylic acid? Again, in every case, what is going to happen? This nucleophile with a H, so the nucleophile going to get attacked here. So once the nucleophile going to get attacked, if you think about nucleophile having a H, then the nucleophile going to get attacked here. There will be minus, which will take the proton. So if you have a thiol, then you end up making this product. So there will be S with aryl. If you have a phenol, then the oxygen going to get attacked. Then finally, it will this proton will going to transfer to that ring to form this product. If you have a corresponding carboxylic acid, what is going to happen? Again, then now you have this the oxygen going to get attack here. Generate this minus, which will be taken by the proton. Again, the Bijou groups, they work in the benzyne chemistry a lot. So they have published in their recent work that if you use this reaction with NN dimethyl aniline. What is happening here? If you use NN dimethyl aniline, again still you are seeing a product here. That means your one of the methyl is getting out and you are introducing one aryl ring here. So they have generated the the benzyne from the corresponding the TMS triplet using the method which was developed by the Kobayashi group using potassium fluoride and 18 crown 6. So here after the benzyne formation, it is happening that so that the nitrogen has this lone pair, it can attack here from this type of intermediate species which can get protons. Okay, so there is a H plus, it can able to get here, get to here. Now you have this fluoride. So if you have a fluoride that can, or if you have base so if you have base of fluoride that can attack here, take this methyl, okay, from this ammonium compound, and then it can cleave this carbon nitrogen bond to get to this product. So in this particular part, I have talked about the different type of reaction using benzyne. So I started with the 4+2 cycloaddition. I told you in most of the cases the benzyne is acting as a dienophile. So now if you take a diene, it will going to participate in 4+2, and all the rules you have learned in the 4+2 still remain same. I talk about some of the in reactions, some of the 2+2 cycloaddition, 3+2 cycloaddition, and again I think in the future slide I am going to talk about more about the some of the arylation and also about the insertion reaction. At the first lecture also I have shown you some references, so please go through this this reference. So there is a very important books by Biju, so you can go through this modern arine chemistry. This is a very nice book to cover the chemistry of arines. Again thank you for coming to the class, and I am going to see you guys in the next class.